Welcome to this lesson on the exponential function e raised to the x. The exponential function is one of the most important functions in mathematics, appearing in fields ranging from pure math to physics, engineering, finance, and even biology. In this video, we'll explore what this function is, its properties, how to graph it, its calculus applications, and why it's so special. But first, what exactly is e? E is an irrational number, approximately equal to 2.718281828459045. It's like pi, a fundamental constant of mathematics that shows up naturally in many contexts. E has several equivalent definitions. One definition is as the limit of this expression as n approaches infinity, the quantity 1 plus 1 over n raised to the power of n. This actually comes from a financial context. If you invest $1 at 100% interest, compounded n times per year, this expression gives your balance after 1 year. As n increases to infinity, continuous compounding, the balance approaches e dollars. Another definition of e is the unique number for which the derivative of e to the x equals itself. We'll explore this property more when we discuss calculus. E can also be expressed as an infinite series. E equals the sum from n equals 0 to infinity of 1 over n factorial. Now, let's graph the exponential function e to the x. Here's our coordinate system. Let's track some points to get a feel for the function. When x equals -2, e to the -2 is approximately 0.135. When x equals -1, e to the -1 is approximately 0.368. When x equals 0, e to the 0 is exactly 1. This is true for any base raised to the power of 0. When x equals 1, e to the 1 is simply e, or approximately 2.718. When x equals 2, e to the 2 is approximately 7.389. Now, let's draw the complete graph of e to the x. Notice how rapidly this function grows for positive values of x, and how it approaches but never touches the x-axis as x becomes more negative. The x-axis, y equals 0, is a horizontal asymptote as x approaches negative infinity. Let's summarize the key properties of the exponential function. Domain, e to the x is defined for all real numbers. Range, e to the x is always positive, taking values from 0 to infinity. Y-intercept, when x equals 0, e to the 0 equals 1, so the y-intercept is at 0, 1. Horizontal asymptote, as x approaches negative infinity, e to the x approaches 0. Always increasing, e to the x is an increasing function for all values of x. Now, let's explore the calculus properties of e to the x. This is where the exponential function truly shines. The derivative of e to the x is simply e to the x. This remarkable property makes e to the x unique among all functions. It is its own derivative. Similarly, the integral of e to the x is also e to the x plus a constant. This is precisely why e is chosen as the base for the natural exponential function. These simple calculus properties make many calculations in mathematics, physics, and engineering much more elegant. The exponential function has countless applications across many fields. In population biology, exponential growth models how populations increase when resources are abundant. In physics, radioactive decay is modeled by e to the -kt, where k is the decay constant. In finance, continuous compound interest uses the formula a equals p times e to the rt, where p is principal, r is rate, and t is time. The exponential function e to the x is closely related to the natural logarithm function ln of x. These two functions are inverses of each other. This means that e to the ln of x equals x, and ln of e to the x also equals x. Visually, the natural logarithm is a reflection of the exponential function across the line y equals x. To summarize what we've learned about the exponential function e to the x, it's defined as f of x equals e to the x, where e is approximately 2.71828. It's graphed as a curve that grows increasingly rapidly for positive x and approaches, but never touches the x-axis for negative x. It has the special property that its derivative equals itself. It has numerous applications in modeling natural phenomena and financial calculations. It's closely related to the natural logarithm function, as its inverse. Thank you for watching this lesson on the exponential function.